Okay, good afternoon, everyone. This lecture is about the momentum as well. Today we will be talking about the types of the collisions, and we will be also looking at conservation of momentum for 2D problems. Okay, so we have three types of collisions that we are interested in this course. The first one is called the elastic. In that collision, we have the momentum and the kinetic energy are being conserved. What does that mean? This means that the momentum before the collision equals to the momentum after the collision, and not just that, the kinetic energy also before the collision equals the kinetic energy after the collision. The second type of collision is called inelastic collision. In this collision, we have the momentum being conserved, which means momentum before the collision equals the momentum after the collision. However, the kinetic energy will not be conserved. Why? Because the kinetic energy some of the kinetic energy will be transformed into another type of energies, and then this is why we call it inelastic. However, the objects that are colliding will be bouncing back. That's why we have a third type of collision that's called completely inelastic. In this case, the momentum will be conserved, kinetic energy will not be conserved, will not be the same before and after. However, both bodies are going to stick together and move with the same velocity. This third type of collisions, we call it completely inelastic. Now let's look at an example of a collision that's bouncing back. And this collision, we need to evaluate the velocity of the blue cart after it bounces back. And also we need to evaluate the type of collision. What type of collision do we have here? So let's start first sketching the before and the after for this problem. Here we have the first cart weighs 2 kilograms, comes with 6 millimeter per second velocity. The other one is 4 kilograms, comes with 5 millimeter per second velocity. They will collide, and then this cart will bounce back with 2 meters per second. We need to know what's going to happen to this cart. So let's start sketching our problem. Here we have the following. If I am to draw the cases I have here, I have here, this is, let me call this one A, this one B, this one is coming with 6 meters per second, so let me call this one VA1. This one is going this way, 5 meters per second. Let me call this one VB1. So this is before. I have the after here. This one bounce back with a velocity VA2 equals 2 meters per second. This one, I have no idea. I will pick this direction, we will see. VB2 is unknown. So the first important thing I need to pay attention to is my positive orientation. So let me take here, this is X positive, this is Y, which is in the east direction. Okay, so Let's write momentum before and after. So here I have sigma p before. This one equals to m. So this is ma. I'll need to write here. Ma is 2 kilograms. Mb is 4 kilograms. So I have sigma p before as ma va1. V is positive minus mb vb1 sigma pb4 equals to ma is 2 kilograms, va1 is 6 minus 4 times 5. This gives me sigma before, sigma p before equals to minus 8. Now let's look at sigma p after. What do I have? I have VA, I have MA. However, this is minus VA2, change direction. I have plus MB, I have VB2 positive. Okay, so this gives me sigma P after equals to minus 2 times 2. So this is the minus coming from the velocity here, plus 4 VB2. This gives me after to be 4 VB2 minus 4. Now let's equate them. I have sigma P before equals to sigma P after. Then this means I have 4 VB2 minus 4 equals to 8. This gives VB2 equals to minus 1 meter per second. As you can see, this is negative, which means it's indeed going not east, going west. So I can say vector wise VB2 vector. Once I say vector, I have to define direction equals to 1 meter per second, and in this case it will be west. So this is VB2 going in the west direction. Now let's evaluate the type of collision we have. So this is A. We found the velocity. Now we need to find the type of collision. We will evaluate the kinetic energy before, which equals to half ma v a1 squared plus half mb v b1 squared sigma ek before becomes half 2 6 squared plus half 4 5 squared, and sigma ek before equals to 86 joules. Let's evaluate ek after, which equals to half 2 VA 2 squared, which is 2, plus half MB VB 2 squared, which is 1, sigma ek after equals 2, 6 joules. As we can see here, sigma ek before does not equal sigma ek after, which means the collision is inelastic. They do bounce back, but they are still inelastic because the kinetic energy is not conserved. Okay. Now let's move on to the next slide. In the next slide, we have the conservation of momentum as well for 2D collisions. In this case, we're not dealing with one dimension. We're dealing with 2 dimensions. So the difference is basically looking at the sigma of the momentum for the x component, that the sigma momentum for the x component before equals to the sigma of the momentum for the x components after. Same thing for the y component. So we will be looking at the decompositions of those vectors on x and on y. So we have velocities that we will be projecting on x and y's, and we will be looking at the momentum before for the x components equals to the momentum after for the x components, and at the same time momentums before for the y components equals to the momentum before the momentum after for the y component as well. So let's look at this example. In this example, we have, as you can see here, billiard game. Two balls from the billiard games colliding with the same mass. We have the cue ball has an initial speed of 1 meter per second. So that's the top view. We're looking here, top view. So we have the cue ball has a speed of 1 meter per second, initial speed 1 meter per second. The 8 ball is at rest, which basically means it has 0 velocity. And then this is after they collide. The cue ball is going to go above the horizon, above this line by 53 degrees, while the black ball is going to go, as you can see, 33 degrees from this line. So what do we need to do here? What are their speeds immediately after the collision? So we know now that those 2 balls, they have the same mass. One of them has an initial speed, the other one was at rest, and then they collide. So let's see how we can solve such a a problem. So the first state here, before I have cue ball coming with 1 meter per second. So let me call this one V1. I have the 8 ball V2 equals to 0. So this is the before. Both of them, they have the same mass. For the after, I have the cue ball going this way with an angle of 53 degrees. However, the 8 ball is taking this path with 33 degrees. So this is the second ball. So here, this is V1 prime for the cue ball. This is V2 prime for the black ball. So let's apply the conservation of momentum for the two-dimensional problem. So here I have sigma p x. So let's pick the coordinates, take the coordinates as x and y. So I have sigma px before equals to sigma px after. I have sigma py before equals to sigma py after. So let me start with the first one. For the before case, I have sigma px before equals to, so the cue ball is going positive in the x direction, so I will write m v1, the other one is stationary, plus 0. So this is the sigma px before. What about the sigma py before? It's 0. Why? Because I don't have a velocity along the y-axis. So now I'm done with the before. Now let's work on the after cases. The sigma px after equals to what? Let's zoom in here and just focus on those two vectors. So the first vector is going this way, right? This is 53 degrees. The second one is 33. So this is V1 prime, this is V2 prime. So if I am to look at the x, this is my x, I can draw this one here as my y. And then let's look at the projections. Let me take the blue as the projections for the V1 prime. So in this case, if I am to project V1 prime on the x, it's going to give me this. So this is V1 prime x. This is v1 prime y. Take the green, v2 prime x, v2 prime y. This is 33 degrees. Now, if I am to write the after, so this is the after now. I'm at the after, focusing only on the x components. So what do I have? I have the b1 x prime being positive. So take a write m b1 prime x being positive. I have v2 prime x also being positive, right? Which is the projection of the v2 prime and the projection of v1 prime on the x-axis. What about the sigma py after? Again, I have the v1 prime being positive, v1 prime y, so m v1 prime y. This one will be negative, right? Because y is positive up, minus m v2 prime y. v1 prime x is b1 prime cosine 53. v1 prime y is v1 prime sine 53. v2 prime x is v2 prime cosine 33. v2 prime y as v2 prime sine 33. Once I have now those ones ready, what's the cosine 53? Cosine 53 is 0.6, right? So what do I have here? I can cosine 53 as 0.6 sine 53 as 0.8. I have cosine 33 as 0.84. I have sine 33 as 0.54. Now let's substitute. Remember, this one equals this one. So I have m v1 prime x which is v1 prime cosine 53.6 plus v2 prime times 0.84 m equals to m v1, right? v1 is 1 meter per second. So I have here m canceling. So I have here, this one is also 1. Then I get 0.6 v1 prime plus 0.84 v2 prime equals to 1. This is the first equation. Got this one. Now the second one equals 0. Sigma py after equals to sigma py before. This is 0. Then I have here m v1 prime y. v1 prime y is v1 prime sine 53 minus m v2 prime y. v2 prime y is v2 prime sine 33 equals to 0. Again, m is going to cancel, and you are going to end up with 0.8, which is the sine 53 v1 prime minus 0.54, which is the sine 33 v2 prime equals to 0. This gives v1 prime equals to 0.54 divided by 0.8 v2 prime. This gives v1 prime equals to 0.68 v2 prime. Let me call this one 2. Now, if I substitute 2 and 1, what do I get? I get 0.6 times 0.68 v2 prime plus 0.84 v2 prime equals to 1, or v2 prime equals to, if you work out this equation, 0.8 meter per second. Now, if we call this one 3, and you take 3, substitute it in 2, 3 and 2, you get v1 prime equals to 0.68 times 0.8. v1 prime is 0.54 meter per second. Okay, now let's move on to this example. If we look at this example, we have pumpkin that being exploded. It splits into three pieces of equal mass as shown here. What is the direction of the velocity of the third piece? So we have the piece number one, they went north. Piece number two went east. And now we need to estimate what is the direction of the piece number three. Now, if you think about it, those two velocities, if you want to look at the equivalent or to add them, they will give you something like this, right? So it makes sense that the third one, due to the conservation of energy, should oppose this direction, right? Which means in this case, E would be the answer to this problem. Now let's solve this problem where we have the same pumpkin and those are three pieces. However, this one has an angle of 22 degrees with the x-axis. We need to find the velocity of the third piece of the pumpkin. If we know that the first one went in the y direction, the second one went 22 degrees below the x-axis, and the second one has a 24 meter per second. The first one has 14 meter per second. We need to find the velocity for the third one. So this is a 2D problem. We will be using the conservation of momentum for 2D problems. Here we have those three pieces. Piece number one going in this direction. So let me call this one V1, 14 meter per second. I have, so if this is X, this is Y. I have this one going V2 as 24 meter per second with an angle of 22 degrees. This is Y. Okay, so they have the same mass. So I have mass being the same for all of them. M. I need V3. Velocity. So if you look at this problem, you have sigma px before equals to 0 because the whole pumpkin was at rest. I have sigma py before being 0 as well. Now sigma px after is, we'll do this one. We'll do this one. by inspection or in a probably faster way than the one we did before. So here, let me draw the velocity v3, something like this. So px after, I have this is v3, and I will call this one theta. So let me look. Let me see here. What do I have? I have on the x. Let me do the x this time with the blue. For both. So this is v3 cosine theta. Cosine theta. This one is v2 cosine 22 degrees. So this is those are the x's. So let me write them. Positive. So I have m v2 cosine 22 degrees. I have minus m v3 cosine theta. So this is for the x. v1 does not have an x component. It is perpendicular on the x. Now let's look at the py after. This one has a component on the y. It's v2 sine 22 degrees. This one also has a component is v3 sine theta, right? So now if I am to write the sigma py after, I have v1 positive, so it's m v1. I have v2 as negative minus m v2 sine 22 degrees. I have this one as negative minus m v3 sine theta. Now, if I am to equate this and this, then what do I get? I get m v2, which is 24, cosine 22. So cosine 22 is 0.93 minus m v3 cosine theta equals to 0. M will cancel. Then what do I have? I have 24.93. If you work out the equation, v3 cosine theta equals to 22.25. So this is the first equation. Now, if I equate this with this, what do I get? I get m v1 as 14 minus m v2, which is 24, sine 22.37 minus m v3 sine theta equals to 0, right? Because this equals to this. This equals to this. M is going to cancel again. And I'm going to end up with 14 minus 8.99 equals to V3 sine theta, and V3 sine theta equals to 5.01. So this is equation number 2. Now if I divide 2 by 1, this one, V3 is going to cancel, and sine theta over cosine theta is tan theta equals to 0.225, and theta is tan inverse of 0.225. Theta is 12.7 degrees, right? Now, if you want to calculate V3, substitute this into here. We get V3 equals to 5.01 divided by sine 12.7. V3 is 22.7 meter per second. This is the magnitude of the velocity. Now, this velocity as a vector is defined by theta 12.7 and magnitude of 22.7. So this is 12.7, and that's the magnitude as 22.7. Last slide is basically a summary example of what we have done so far in terms of using the conservation of energy and using the conservation of momentum. In this example, we need to calculate the height h for a sphere A that has, this sphere A has mass of 71, starting from rest, is going to collide with sphere B, was a mass of 55 and also stationary. Once they collide, they become completely inelastic in their collision, which means they will become one mass, and they will go with a velocity of, or a speed of 5.8 meter per second. So once we see a collision, this means we will be using the conservation of momentum. So the problem would be formulated this way to calculate for the height. Right now, skier B is stationary. Skier A is starting from rest, then he will come all the way till he gets to this level. At this level, right before colliding, he will be at y equals to 0 before colliding. So the maximum speed, he will get it right there just before colliding with him with a skier B. Now from this collision, we can extract the speed of skier A right at this point, and this is going to be, we can find his kinetic energy. Right at this point, his potential energy is 0 because he has reached level y equals to 0. Then right at this point here, when he's at rest, he has a kinetic energy of 0. He has only potential energy. Right here before colliding, he has a potential energy of 0, and he has only kinetic energy. Then from the conservation of energy, we can find the height. We'll see how we can do this problem. Okay, so in this problem, we have before both of them, B and A, just before they collide. So this is A. We have V B1 0. We have V A. Let me draw this a little bit. This is where he gets the maximum velocity. So we have VA2 unknown. This is my coordinates, X and Y. The after, they will become as one mass, right? So I have MA as 71 kilograms. I have MB as 55 kilograms. And then they will go with a velocity. Let me call this one VAB equals to 5.8 meter per second. So sigma PB4 equals to MA VA2 plus 0, because the speed for skier B is 0. It was at rest. Sigma P after as MA plus MB times VAB. Now, conservation of momentum, they are equal. Then I have MA plus MB VAB equals to MA VA2. So I have 71 plus 55 times 5.8 equals to 71 times VA2. VA2 equals to 10.3 meter per second. So this is the maximum velocity, the maximum speed, right at the y equals to 0 for skier A, right before colliding with the skier B. So we found his speed right at this location. Now let's go back to skier A. He is starting from here. VA1 was 0. Now he's going to go to y equals to 0. Again, this is y, this is x, this is y. This level as y equals to 0. Now I know his velocity here, VA2 equals to 10. His speed is 10.3 meter per second. His speed here is 0. I need this height. So how do I calculate this? From the conservation of energy, I know EK A1 plus EP A1 equals to EK A2 plus EP A2. Now the potential energy, the gravitational potential energy right here is 0. The kinetic energy right here, because the speed is 0, is 0. So I ended up with EPA1, which is M A G Y 1 equals to half MA V A2 squared. MA is going to cancel. Y1 is the H that I am after. Then I have GH equals to half VA2 squared. And H equals to VA2 squared divided by 2G. And H is VA2 squared is 10.3 squared divided by 2 times 9.8, and H is 5.4 meter.